So we'll start by taking a derivative with respect to time of y equals 3x squared. Derivative of y is just dy dt. Derivative of 3x squared is 6x, but not just 6x, because we're taking a derivative with respect to time, so dx dt. On the other one, how am I going to do 3xy? What rule is that going to require? Product rule. So I'm going to and derivative of x squared with respect to time is 2x dx dt. Again, what you're taking a derivative with respect to matters, and that's usually why we stop using y prime so much, because y prime is usually dy dx, and that doesn't really have a use in these problems. Okay, dy dt, that's a rate. That's a rate of change of y. Dx dt, that's also a rate. That's a rate of change of x. So how is y changing versus how is x changing? You put those two things together in one equation, and now you've got related rates. So related rates just means your answer, or maybe not your final answer, but some part of the problem is going to have multiple d dt problems in it. So you're going to have dx dt and dy dt, or dr dt, dv dt, dh dt, everything that could change with respect to time. Lengths, widths, heights, radiuses, volumes, speeds, like all sorts of things. Related rates. Related rates are applications of implicit differentiation. Often we're finding the rate of something with respect to time. So most of the time t is our independent variable. And so we don't often use y prime today, because y prime is dy dx, and we don't usually want dy dx. We want dy dt or dx dt. Okay. Again, we've kind of done this, so I think we'll start off easy, I hope. Suppose y equals 5x squared minus 6x plus 2. Find dy dt when x equals 4, given that dx dt equals 2 when x equals 4. It's like, holy cow, that's a lot of information to get through. But let's start with find dy dt. Well, let's start there, and then we'll figure out the rest. So if I want dy dt, I need to take a derivative of this thing with respect to what? With respect to t, so the dy dt shows up. So again, the step that you're probably not going to show very often, but I'm going to take the derivative of both sides with respect to time. I will almost never show that step after this problem. But it's important to remember that's what we're doing. Again, most of the time you skip that step and you jump straight in and say, okay, dy dt equals, and then on the other side, let's pick on some people. Let's pick on 3 different people, in fact. Austin, Jake, and Jace. So Austin, the derivative of 5x squared with respect to time.
So it's 10x and then dx dt.
Good. Would you like to make a guess at what most people miss when they're taking a derivative with respect to time of 5x squared?
They don't do the dx dt.
That's exactly right. They forget about the dx dt. Like, they know the derivative is 10x, but they'll leave off the dx dt. All right, Jake. Austin laid a nice example for you here. How about the derivative of negative 6x?
Negative 6 times dx dt.
Negative 6 dx dt. And Jace, the derivative of 2? 0. Okay, so I found dy dt, but now I want dy dt when x equals 4, given that dx dt is 2 when x equals 4. Okay, this is ugly, but they're giving me all the pieces. So maybe it's not as bad as it initially looks. X is 4, so 4 will go in for X. dx dt is 2, so 2 will go in for dx dt. So let's see what happens. So 10 times 4 times 2 minus 6 times 2. And well, that's a safe stop, so I guess you could just leave it at that. Let's see, 80 minus 12 is 68. But any of those stops along there would be correct. One small thing about notation, I should probably put that bar right there and x equals 4. That means dy dt at x equals 4. It just says I'm plugging in x equals 4. Okay, so the old stuff is taking a derivative with maybe d dt rather than dx. So implicit. The new stuff is there's going to be some word problems and we're going to plug some things in. Example 2. A pebble is dropped into a calm pond causing ripples in the shape of concentric circles. Right, you've done that. Throw something in, watch the circles gradually spread out. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, find the rate at which the area of the circle is changing. Oh, we've got to interpret what they're giving us and what they're asking for here. The radius of the circle is increasing at a constant rate of 1 foot per second. So something is 1 foot per second. But what variable is equal to 1 foot per second? What am I going to set equal to 1 foot per second? Let's use radius. But the radius isn't 1 foot per second because the units don't even make sense for that. The rate of change of the radius, yes. And how do we say, or what do we do for rate of change? dr dt. Change in r over change in t. dr dt is the rate of change of the radius with respect to time. So it's a mouthful to get out dr dt. Again, be careful with units. The units can help. You can't say the radius is 1 foot per second because radii don't have units of feet per second. When the radius is 4, okay, so there's an easy one. When r equals 4, find the rate at which the area is changing. Okay, rate is the giveaway that its a derivative is involved. So what are we trying to find? Find the rate at which the area is changing. Say it louder. No, you were having it, I think.
DA. I don't know what it's over.
Okay, well, you're on the right track. dA, that would be the rate at which the area is changing. You know what? It might have been better if they'd have said with respect to time, because that would have been a little clearer. That is time. For us, I think I can say all the denominators. That's not a fraction, so I shouldn't call it a denominator. All the bottoms are going to be the same. You're not going to take a derivative with respect to x, and then a derivative over here with respect to y, and then a derivative over here with respect to time. For us, they're going to be the same bottom term. Okay, so that means now I need some equation that relates area and radius. Can you think of an equation that includes area and radius? What would that be? Should pull a popsicle stick for that. 7th grade, 6th grade, 8th grade, whatever it was. What is it? Pi r squared. Area equals pi r squared. By the way, if it's a complicated equation, and it doesn't even have to be that complicated, like you can take a peek ahead at number 3. Volume of things and surface area of weird things, like AP will usually give you the formula, even if it's one that math teachers would be like, come on, they know the volume of a cylinder. Students are probably like, no, we don't know the volume of a cylinder. Anything beyond like basic area of a square, area of a rectangle, area of a circle, like they expect you to know that. But anything a little more complicated than that, they'll start giving it to you. So I don't think you're going to have to memorize any new geometric formulas for this unit. We're going to assume you got pi r squared down. Okay, I'd like dAdt to show up. So what should I do to make dAdt show up? Take the derivative. I said I wasn't going to write this step again, but I'm going to do it one more time. I'm going to take the derivative with respect to time of both sides. Right, so dAdt on the left, on the right. Lexi, how about the derivative of pi r squared with respect to time? Very nice. 2 pi r dr dt. And again, the leaving off the dr dt is the mistake, the frequent mistake. Okay, so I want to find dAdt when r is 4. dAdt when r equals 4. When r is 4, well, 4 will go in for r. And the RDT, we said, was 1. So that would be 8 pi. But I wonder what the units are for dAdt. There's 2 ways to get units. You can use either side of the equation to get the units. Probably the best way is to use the left side of the equation, because you don't really have to do any math. You just have to know what are the units for area. If we're dealing in feet squared, and what are the units of time? Seconds. So dAdt would have a unit of feet squared per second. So this means the radius is expanding at 1 foot per second, and as it's doing that, that means the area is getting bigger at 8 pi feet squared per second. So what is that? 8 times 3 is 24 plus a little bit. So like it's adding 25 square feet every second when the radius is 4. That changes when the radius is changing, so that's not a constant dAdt, but when r is 4, the area is changing at a rate of feet squared per second. We can check the other side. I only plugged in the numbers. I didn't plug in the units. But you can also get the units by plugging in the units. So 4 feet times 1 foot per second is feet squared per second. But that's kind of the harder way. The easier way is to just, you want A over T, so it's got to be feet squared per second. Units are only needed when asked for. Units are only needed when asked for. That goes for the AP test as well. And that also means when they do ask for them, there is a point assigned to them. And so even if you can't figure out anything else, if you just put dAdt equals make something up and put feet squared per second, you would get 1 point for that because at least you understood what the unit should be. So that's good news. Like when you get to some crazy, part E of the last free response question on the AP test, and it's something crazy, but if you can figure out the units, maybe you can squeak out a point. So if they ask for it, make sure you give it because there's a point attached to it. If they don't ask for it, you don't have to give it. And I guess the other good news is if they don't ask for it and you give it wrongly, they won't count it. They won't count off because it wasn't part of the question. Number 3. Water runs out of a conical tank at a constant rate of 2 cubic feet per minute. Let's just read the whole question, then we'll go back and draw pictures and identify what's going on. Water runs out of a conical tank at a constant rate of 2 cubic feet per minute. The radius at the top of the tank is 5 feet, and the height of the tank is 10 feet. How fast is the water level decreasing when the water is 4 feet deep? And there's the volume of the cylinder. All right, well, while our brain kind of processes this problem, maybe we can draw a picture of what this looks like. So we got water in this tank. Our water level, maybe. I don't know if it's dripping out or streaming out. I don't know. 2 cubic feet per minute. Cubic foot. 2 of those every minute. I don't know. It's a steady stream. It's not a fire hose, but it's more than a drip, I think. What is 2 cubic feet per minute? So what did they tell us here? Again, the units will help. The fact that it says rate will help. So what is 2 feet cubed per minute? What variable is that? It's a rate, it's a derivative. Feet cubed is a volume. So dV dt. So the change in volume is 2 cubic feet per minute. Let's see, the radius at the top of the tank is 5 feet. And the height of the tank is 10 feet. So that's not like how much water is in there, that's just like how big the tank is. How fast is the water level decreasing when the water is 4 feet deep? What's it asking for? How fast is the water level decreasing? So what variable is that? Find. It's related to height, but it doesn't say how high is the water because the water is 4 feet high. But height measures the water level, so you're close with height. No, you're close with height. You're close with height, but the height is changing. So the decreasing part means I want to know how the height is changing. So let's find dH dt. It will be feet per second when we get there. So I want to find dH dt when h equals 4. Okay. And they're nice enough to give me a equation here. Okay, they gave me dV dt, so that'll show up. When I take a derivative, dH dt will show up. Uh-oh. What else is going to show up if I take a derivative of the right-hand side? The RDT is going to show up. And I don't have the RDT, and I don't really have anything that tells me the RDT. It would be really nice try, and you can almost always do it in here, try to make your equation have only two variables. Try to make your equation have only two variables. That way you get away from product rule and quotient rule and extra drDTs thrown around in there. So it would be nice if we knew some relationship between R and H so that that R could go away. I really don't want R in there. So if I could come up with something about R, man, life would be really nice, because then I could have an equation without an R in there. Okay? So R is 5, but that's only at the top of the... So that's a great point, because you can plug things in if they're constant, but R is changing, right? As we drain out, the R is getting smaller. So I don't want to plug in 5. Don't plug in things unless they're constant. So R is 5 at the top, but I don't want to do that. Jake, what are you saying?
H.
Where did you get that from?
Because R is 5 and H is 10. So it's like H.
R is always going to be half of H. Like, as this thing drains, whatever this is, I guess we could say that that's when it's 4 feet deep, then H would be 2. Like, the ratio continues. R is half of H. So that's really good news. I mean, it's going to make the algebra kind of ugly, but it's going to be great for the calculus. So I'm going to replace R with half of H, because then I'll have only one variable left. E equals 1/3 pi times half of H squared times H. Okay, let's clean this up a little bit. Half squared is a fourth, so 1/12 times pi times H cubed. That's the volume of the cone. And we got rid of R. So now we can take a derivative and we'll have dH dt show up, and we'll have dV dt show up, but that's fine. Those are the two quantities that I care about. Like, I know dV dt, I'm looking for dH dt. So let's take that derivative and see what happens. So dV dt equals, let's put somebody on the spot for the right-hand side here, Aslan. What does the right-hand side become after I take a derivative with respect to time?
1/12 pi, or 3/12 pi H squared dH.
Nice. 3/12 will reduce, but we don't have to worry about that yet. Okay, I think we're almost there. Now we can plug all the pieces in, because we know dV dt. We have H, 3 pi and 12, that's all constant stuff. And we're looking for dH dt. Okay, I guess we could solve for dH dt first, but it's probably better to plug in first. dV dt, is 2. No, I think I misled you a little bit on that. Water runs out of a conical tank. So what's happening to the volume of that tank? It's decreasing, which means dV dt is negative. What do we think dH dt is going to be? Positive or negative? It's going to be negative. As it drains out, H is getting smaller. So I'm expecting dH dt to be negative as well. We'll find out. So negative 2 equals pi over 4. H is 4. And then dH dt is what we're looking for. Negative 2 equals the 4, one of them cancels, so 4 pi dH dt. So dH dt, divide both sides by 4 pi. Negative 2 over 4 pi. Say stop. I mean, yeah, it reduces, but why bother? And then it didn't ask for units. And this would be a lot of units to keep up with, but if we use dHdt to get the units, Ashlyn, what do we think the units of dHdt would be? What's h measured in? Just feet. And what's t measured in? Seconds. Minutes. So that means the height of the water is decreasing at whatever that is, feet per minute. So every minute it goes down this many feet. That's how fast it's going down. I'm not going to box the units because we didn't ask for the units. Alright, let's do one more. We'll save the two of them for... Yeah, we're good. We'll save 5 and 6 for tomorrow. This should probably be a starred problem because the ladder problem is every year on a test, at least my test, and then frequently on the AP test. So it's an important problem. A 13-foot ladder is leaning against a wall. Suppose that the base of the ladder slides away from the wall at a constant rate of 3 feet per second. Okay, so not good news if someone's standing on the ladder, starting to slide down the wall. How fast is the top of the ladder sliding down the wall when the base of the ladder is 5 feet from the wall? Ugh. Indicate units of measure, so I do need units on this one. Okay, so there's my 13-foot ladder leaning against the wall. The base of the ladder slides away from the wall at a constant rate. So the base of the ladder slides away from the wall at 3 feet per second. I'm not putting variables on that yet. I think I just want to label it. What's happening? It's sliding out down at 3 feet per second. So I think you can see if the ladder's sliding down, or sliding out, then the top is sliding down, and that's what we're looking for. Is what is that thing? How fast is that going down? How fast is the top of the ladder sliding down the wall when the base of the ladder is 5 feet from the wall? I don't really want to label this as 5 because that's changing. So I don't want to put a 5 on there because that's not a constant, that's a variable. We want to know it when it's 5, but it's not always 5. Okay. Anybody know an equation that relates the three sides of a right triangle? Yep, Pythagorean theorem. A squared plus b squared equals c squared. Okay, let's see. I guess we should label these. Doesn't really matter which one we call A and B. I'm going to call the bottom A and the side B. And hypotenuse, well, I guess it does matter which one the hypotenuse is. That one's got to be C. C is constant. So we only want one variable, or two variables, excuse me. But we can get rid of C because it's always 13, right? As the ladder slides down, the ladder's not changing length. Now that I've got this labeled, if this length is A, what is 3 feet per second? What variable should I call that? So A is the distance from the bottom of the ladder to the wall. That distance is increasing by 3 feet per second. So what is 3 feet per second in terms of variables? It's a rate, something's changing. It's how A is changing, so that's dA dt. So this one's tricky because they didn't really spell out what that was. We had to draw a picture, come up with our own variables, and then realize it's dA dt. What are we trying to find? I mean, there's my picture, what I'm trying to find, but what is that? What dV dt? And we want to find that when something is 5 feet from the wall, so that would be when A is 5. Right, well, if I want dA dt and dB dt to show up, I should probably take a derivative of this thing. Well, 3 terms, 3 people. Jameson, if I take a derivative of that thing with respect to t, what's the derivative of a squared with respect to t?
2a dA over dt.
Good. Small side note here, she said dA over dt, and that's fine, but we'd like to emphasize that this is not really a fraction. It's one quantity. It's dA dt. So if you say dA over dt, that's okay, but be careful, it's not a fraction. It's one quantity, dA dt. James, how about the derivative of b squared with respect to time?
Is it 2b dB dt?
Very nice. And Ben, how about the derivative of 13 squared with respect to time? 0. Good. I tried to trick Ben, but he would not be tricked. I wanted him to say 2 times 13, but that's not right. Well, you could say 2 times 13 times the derivative of 13, which is 0. He was not fooled. Okay, do I have everything I need now? I've got dA dt. I've got A. I'm looking for dB dt. Uh-oh, I'm missing B. I'm going to need B in order to solve this. Well, A is 5, C is 13. Geometry all-stars. Yes, Seth, say it. 12. 5, 12, 13. I mean, the AP test is hard enough, but frequently they throw little things in like that, where I guess if you forgot it, you could still do, a squared plus b squared equals c squared, but hopefully you would remember 5, 12, 13. So when A is 5, B is 12. Okay, so we're ready to plug some things in now. I could divide by 2 and make all that go away, but oh well. 2 times A is 5. dA dt is 3. Trying to keep up with all the pieces here. 2 times B was 12. dB dt is what we're looking for. And that equals 0. Let's see here. Let's be lazy and do a safe stop. So I'm going to subtract over the 2 times 5 times 3 and divide by 2 times 12. Right, if safe stops are okay, then use them. It does say indicate units of measure. So I could put all the units in there and then do some unit algebra, but I don't really want to do that. I'd rather just look at dB dt. What is B measured in? Feet. And what is T measured in? Seconds. So feet per second. That makes sense. It's negative though. Does it make sense that it's negative? It's going down the wall, so B is getting smaller, so that's why it's negative. That's a perfectly okay safe stop. I think it reduces to negative 5/4, but we're not worried about that. Like, that's enough. Okay, today's assignment, worksheet 2, let's try just 1 through 5. 1 through 5. And some of those are pretty straightforward, not even word problems. And then 5 is pretty close to the same example. I think it gives some...
It's the same number.
it's not exactly the same numbers. Yeah, it's not the same number. Looking at number 5, now we know that the top of the ladder is sliding down the wall at 2 feet per second. So we've sort of changed up what we know, but it's definitely the same type of problem. So, try 1 through 5. tomorrow I'll work some of those. We'll work examples 5 and 6, and we'll do some more examples from the worksheet.
But